Oh, so I'm going to do problem 57 of chapter 8. And in this one, we have a spring that's 20 centimeters connected to a 30 kilogram block, which is attached by string to a 20 kilogram block. Then, this is pulled up 20 centimeters, so this goes 20 centimeters down this way, and they're released. And we're set to find the speed of the blocks when this goes back to 20 centimeters. So we're going to use the conservation of energy here. So for the initial setup, we have kinetic energy, the spring potential, and gravitational potential. And similarly in the final, we'll also have kinetic energy, spring potential, and gravitational potential. And for the gravitational potential, I set that when the spring is 20 centimeters, that's going to be the 0 for block B, and that's also going to be the 0 for block A. So this means that we have, for the initial energies, 1/2 mass of A times V squared plus 1/2 mass of B times V squared plus 1/2 kx squared plus mg HA plus mb times gravity times h of B. And then similarly, we'll have those for the final. However, at the final, this is back to 20 centimeters. So that means that these two blocks are going to be at the ground, so they're not going to have any gravitational potential energy. So plugging in numbers, we know that the initial velocity of these blocks is 0, so the kinetic energy won't matter because it's 0. And then we know that the spring potential, because this is pulled up 20 centimeters or 0.2 meters, it's 1/2 times 250, which is the spring constant, times 0.2 squared. And then for the gravitational potential of A initially, this is down 20 centimeters. So we only need to care about the h distance, which would be 20 times sine of 40, because this angle right here is 40, and it would be negative because it goes below. And then the potential energy, gravitational, of block B is going to be 20 times its mass, 20 centimeters, which is 0.2 meters, times its mass times 9.8. This is because it's pulled up 20 centimeters. And then this equals just 1/2 times the mass of A times V final squared, plus 1/2 times the mass of B times V final squared. Because at equilibrium, there's not going to be any of the stretching of the spring. So then, setting these equal to 0 because they're not moving initially, we have 1/2 times 250 times 0.2 squared minus 20 times 9.8 times 0.2 times sine 40 plus 30 times 9.8 times 0.2 equals 1/2 20 plus 30 times V final squared. And here I just combine these two terms. So then, using the calculator to simplify these expressions, we get 5 joules minus 25.197 joules plus 58.8 joules equals 1/2 times 50 times V final squared. So then simplifying this, we get 38.603 joules is equal to 25 V final squared. So V final squared is equal to 1.544, or V final is equal to 1.24 meters per second.